All right, uh, we'll get started today. So, thank you, Krishna Kumar, for joining. Um, I guess others are going to watch it in YouTube. That's all right. So, if when you watch, if you have any doubts, feel free to, either. Uh, I mean, you're always welcome to attend this session. But if you're not comfortable with the timings, or if you're busy, probably your mid-semester exams would be going on probably. um, you can always come in next uh, week and you can ask your doubts, or you can even email me. I think one of the weeks I've already shared you my email. Also, you can use the common forum, which would be very useful. So even if you don't understand, there will be other students who might understand the concepts and they will be able to help you with it. If I get a if I you know uh, see one of your doubts, I would also would be able to uh, resolve it. Uh, Nevertheless, I always would encourage you to attend these sessions. And yeah, without further ado, let's get into today's this week's content. So let me quickly give you a recap of what we did. And last week I think we slightly touched about infinite slab. And then this week I think we studied about semi-infinite slab. And we also studied a bit about convection. I mean, we studied more about convection, but in our assignments, this week's assignments, the convection is not there. So let's quickly go through what we studied. So we initially started with the transient heat conduction analysis. In transient heat conduction analysis, first we worked on a lumped capacity model, a lumped heat capacitance parameter, where you consider the entire object with one uh, temperature without any spatial variation of temperature field. You consider it, everything will be as the temperature variation within that object would be minimal, or it will be very less, or it is isothermal. The whole object is isothermal. If that is the case, how would you perform a heat conduction analysis is what we studied, transient heat conduction analysis. And then we relaxed that assumption in this 1D unsteady steady state unsteady state heat conduction. um, that's what we studied. Initially, we studied for infinite slab. Then the other thing is we studied for semi-infinite slab. Um, the governing equations we already know. I think we studied in week 1, 2 itself. Only thing is, how do you solve this governing equation? Because these are partial differential equation. It's not an ODE, uh, in which you already know uh, how to solve an ODE. But this is a partial differential equation, so we need certain uh, methods to solve this partial differential equation. And one of the method that we studied is separation of variables. We separate, basically we say that the temperature field is nothing but uh, multiplication of two functions, where one is a function of x, the other will be a function of time, because we have two independent variable, one is x and t. So we decompose it like this. And then if we assume this is the function, then this is how the temperature profile looks like. Then if we try to solve it, we will end up having an eigenvalue problem. And we go through a lot of mathematical step, and then finally we arrive at the solution. So our solution would look something like this. The theta is equal to some constant times summation of a lot of variables. Now to find this constant, you find something called orthogonality condition, and then you simplify it. This is what we studied. I think this was taught in last week itself. And we actually extended it uh, for different analysis. Let's say like you have a, instead of specified temperature boundary condition, let's say if you have a convective boundary condition, what would happen? And similarly, and then it finally ended up with the same solution. Okay, same solution in the sense similar solution, but the eigenvalues are a little bit different. Eigenvalue now is an transcendental equation which you will solve for to find the lambda m. Once you find the lambda m, you use it here to find the constant. Once you find constant, you can find the entire solution field. Okay, similarly you have transient heat conduction for semi-infinite medium. Let's say it is not infinite in the y direction. Now it is infinite even in the x direction, but one side we know the boundary condition, the other side it tends to infinity. So when we have such a semi-infinite medium, then how will you perform analysis? Similarly, we were introduced into similarity parameters. I think this similarity parameter you would also study in fluid mechanics, especially in the boundary layer uh, concepts. You will end up having similarity solutions there too, right? Here also it's a similar approach. Mathematically there is no difference. Only thing is where there also, if you see, you have a flat plate and you have fluid flowing around it, so it's like semi infinite medium. We don't know what is the bound on the other side, right? So in those places we have this similarity solutions. It's also similar to it's basically same as separation of variables, but we know one of the function. In separation of variables we don't know the function, but here we know one of the function, which is the variable itself. That's what the difference is. Anyway, you go through a lot of steps, and everyone must have gone through the videos, and then you finally end up having solution. So all this mathematics, please understand, is to solve this partial differential equation. So one thing what you need to know is, how do I end up, so this mathematical analysis you can always perform. You just need to learn some I5 mathematics, and then you can apply it, and then you can get a solution. This is not the only way to solve this problem. You can have multiple mathematical tools you can use to solve this. But one thing you need to remember is, you should know the governing equation, the governing differential equation, basically the partial differential equation that you derive from the energy equation. So that is something you should be very good at in deriving it. If you derived it properly, then you can even do a numerical analysis to get this profile. So that is not a very big problem. The only understanding that you will try to get is while deriving the governing equation. So which is what this equation is: your governing equation, your initial condition, and boundary condition. This is depends upon the problem, and you should be able to derive this governing equation. Okay, that is something I would you know uh, uh, tell here. Okay, and then we also did a little bit about convection, and it is going to continue in your next week also. What I would suggest is you go through the convection part, um, although it is not fully relevant in this week's assignment, so I'm not going through it. Maybe we will, once you go through the entire convection part, maybe I will uh, uh, show you what are some important things that you need to take away, and you should remember. Okay. All right. With that, that is what we did this week, and with that, we'll enter into today's question. So ideally, I have like one question only, but this question is divided into two parts. That's the difference. And this question is about, again, transient heat conduction. This we A similar problem we already solved last week, but in the last week we had like sphere, and we just directly used the transient heat conduction equation. If you remember, exponential of minus HAS by rho CT, rho CV times T. We directly used that equation, we simplified it, and we solved, and we got the results. But what if there is more general, equation, more general problem, right? For example, if you have you do not have a sphere, instead you have something like a rectangular or cylinder, and there is some heat generation happening within it. If you have such complications, how will you perform a transient heat conduction analysis? Again, we are going to restrict ourselves here with the lumped capacity model, because we do not really want to go through all the mathematics that we derived in the in the class. Okay. um, and it is also not very useful in that way. So semi-infinite, infinite slabs, all these problems we could solve, uh, but it it may not have enough uh, physical significance unless you do a 2D approach. So anyway, but you are welcome to refer the books. Uh, I think the book is Incropera's Heat and Mass Transfer. You can go through the book, solve few more problems if you are interested in semi-infinite and infinite slab problems. And if you want to learn more about it, you can let me know. I can also do some work on that. Okay. All right. With that, let's get into today's problem. What we have here is this is about electronic cooling. I think we already solved one such electronic cooling problems maybe in one of the previous weeks. Here also a similar problem. A chip, this is a computer chip, a chip that is of length 5 mm on a side and thickness of 1 mm is encased in a ceramic substrate. Okay, and it is exposed, and its exposed surface is convectively cooled by a dielectric liquid for which H and T infinity is given. So basically you have a chip and it also has some thickness, but it is enclosed or encased in the ceramic substrate. So which means only top surface is available, and that surface is cooled. Okay, basically since it's a chip, it is going to generate heat, and heat has to get out of the chip in order for it to function properly. Or basically the temperature of the chip, as we have to maintain the temperature of the chip to a certain level. It cannot exceed, let's say, like 70 degrees Celsius or 60 degrees Celsius. Okay, so what we do is we do cooling. Here we are using liquid cooling. We are using dielectric liquid whose convective heat transfer coefficient and the temperature of the fluid is given. Okay, so in the off mode of the chip, which means it is not working, it is in thermal equilibrium with the coolant, which means the coolant and the chip are in the same temperature, which means initially at T equal to 0, it is in thermal equilibrium with the coolant, which means the chip is at 20 degrees Celsius at T equal to 0. Okay, when the chip is energized, or which means you are switching it on, however, its temperature increases until a new steady state is established. Okay, so it slowly increased to a steady state value. Probably we solved steady state, similar steady state problems before, but now we are interested in transient analysis from initial condition to steady state, how it is going. Okay, for the purpose of analysis, the energized chip is characterized by uniform volumetric heating. Okay, there is a heat generation. Assuming an infinite contact resistance between the chip and the substrate and negligible conduction resistance within the chip, determine the steady state chip temperature. So initially they want to know what is the steady state chip temperature, and following the activation of chip, how long does it take to come within 1 degree Celsius of the temperature. So basically they are asking, now initially my temperature of the chip, let's say it is at 20 degrees Celsius, and when you switch it on, it's going to heat is going to get generated. If heat is generated within the chip, its temperature is going to increase. So it can increase however it wants. So and then it finally reaches some steady state. So this is the steady state value, T steady state. Okay, now if it has to reach this steady state, uh, so first they are asking what is the steady state temperature, and now uh, so this is with respect to time. Okay, this is with respect to temperature. So at some point this has reached steady state. Now if it is 1 degree less than steady state, how much time does it take? So what is this delta T to reach 1 degree less than the steady state value is what they are asking. So they wanted to know what is this time, uh, how much time does it take to reach near the steady state value is what they are asking. Okay, so this I draw for your understanding. I hope the question is clear. So we have to calculate two things. One is steady state temperature, another is uh, time taken to reach 1 degree less than the steady state temperature. All right. So maybe let me draw this again for better clarity. So you have a substrate and then you have a chip over here. This is the chip. So its length over this way is 5 mm. In fact, it's a square chip. So 5 mm cross 5 mm will be the area. And this is the thickness, which is 1 mm. And this is the substrate. This is chip. Okay. So this surface over here is exposed to fluid, at 150 watt per meter square Kelvin, and temperature is 20 degrees Celsius. And what is also given is q dot generation, which is 9 megawatt, which is 9 10 power 6 watt per meter cube. So this is the q dot generation, and chips density is given 2000 kg per meter cube, and Cp is 700 joules per kg Kelvin. Okay. All right. I think everything is taken into account. Only thing we need to find out is, two things we need to find out is T of the chip. Okay, maybe I will just call it T. So what they have said is T at T equal to 0 is T infinity, which is 20 degrees Celsius. Okay. Now I want to know what is T steady. Okay. Number 2, I want to know what is the time taken to reach T steady minus 1 degree Celsius. This is what, or maybe I will just write it as T. Okay. So what are these is what they are asking. Okay. I think first thing we can easily find out, we just need to perform a steady state analysis. But what I would suggest is, as I said before, we need to know how to make this governing equation. How would you properly remove certain terms, and how would you make sure that this problem follows this governing equation? Okay. Once you have that, then you can perform certain assumptions and you can remove certain terms, and then you can solve that equation to get the solution. Okay. So let's say let's assume it's a transient analysis. So if you want to know a steady state condition, you just remove the unsteady part in your transient equation. That will give you the steady state solution. Okay. So in that way, let's say if you know um, derive a transient heat conduction equation for this, that should be enough. So how would you do it? Transient, maybe transient, yeah, I would say instead of conduction, I would say transient heat transfer analysis. Okay. So basically, if you want to perform such an analysis, you need to know the system. You need to first determine the system. In our case, we are interested in temperature of the chip. We are not interested in how substrate reacts or so what is happening in the substrate. We are interested only in the chip. What is the temperature? How much time it takes to reach a certain steady state temperature? What is that steady state temperature it reaches finally? Is what we are interested. Which means our system is this. Okay, it's just the chip. Okay, and we all studied energy balance, and what the energy balance says, E dot in minus E dot out plus E dot generation is equal to E dot stored. Okay, so this is the general energy equation. From here only we started deriving, and then we ended up having different heat conduction equation at different coordinate systems, with generation, without heat generation, all these things, everything started from this place. Okay. um, so we so I'm going to take a bigger step over here. We know what is E dot stored, right? The energy stored is nothing but rho Cp V times dt by d. Or maybe what I will do, I'll just directly write the equation. So rho Cv, V is the volume here, dt by d is equal to E dot generation, which I'm going to write as Q dot generation. Q dot generation is per unit volume, so we need to multiply by volume. Okay. And then what are the uh, heat transfer going out of the system? There's a convective heat transfer going out. There is also conduction happening here, here, and here. Okay. Ideally, what they have said is assuming infinite contact resistance, which means there's an infinite resistance to heat transfer between chip and the substrate, which means from chip to substrate there is an infinite resistance, which means there is no heat flowing along from chip to substrate. Okay, so we are going to make that assumption, which means we have only one heat transfer, which is the convection heat transfer, which is going to be exposed on top of the chip. So that would lead to reduction in the energy storage, which will be HAS T minus T infinity. Okay, so this is basically E dot out, right? And this is basically E dot generation. There is no E in, because the chip is going to be at higher temperatures, so every energy is going to go out, and this is E dot store. And I really hope that this shouldn't be a surprise for you. I hope everyone knows these terms. So basically, this is what we are doing. Now we will just simplify this for different cases. One is we want steady state values, so we will just make a steady state assumption. We also need transient. We need to know time at which it reaches steady state. So that is also we are interested. So at that time we will keep the transient term. That's all. So you will have one equation. You simplify it for steady state. Okay. So let's say let me simplify it further. D by dt is equal to, so Q dot generation divided by rho C. So VV gets cancelled, minus HAS by rho CV T minus T infinity. So this is your final equation. And if you are able to get this equation, the problem is solved. Okay. Now first thing we want to find is steady state temperature. How would you do the steady state temperature? We'll just make rho CV dt by dt equal to 0, or in this case we will just make dt by dt equal to 0, right? There is no change. So this, the same equation will simplify to Q dot generation by rho C minus HAS by rho CV times T minus T infinity equal to 0. Okay, so this rho C is common, so you can simplify that too. It just becomes Q dot G is equal to HAS by V T minus T infinity. So this becomes, we want temperature. So if you want to rewrite this, become Q dot GV divided by H into AS plus T infinity. That's all. Okay. This is your steady state temperature. We could call this, how are we calling this? T steady. Because we neglected the transient terms. Alright, I hope it's clear till now. Now we need to find what is volume, we need to find what is surface area. We know the surface area is for the convection, and the convection is happening in that square plate. So it will be 5 mm cross 5 mm. So this is the plate in which the convection is happening. So it's nothing but L square. So this is L square, and volume is nothing but this surface area times the thickness, which is 1 mm. So this is nothing but 5 into 5 into 1, which is 25 mm cube. This is 5 into 5, which is 25 mm square. Okay. Q dot G is given, H is given, T infinity given. You can directly find T steady. How much would that be? So Q dot G is 9 into 10 power 6 times V is 25 into 10 power minus 9, because you need to convert everything to SI units. Here it's meter cube, and H is 150 watt per meter square Kelvin, and area is 25 into 10 power minus 6. Okay, so now, okay, one more thing, there is plus T infinity. You need to add this T infinity, which is 20 degrees Celsius. You can add it as Kelvin, you can add it as degree Celsius, doesn't matter. So if you perform this analysis, how much would you be getting the steady state temperature to be? If you guys have the calculator with you, then please let me know. So I'm also calculating here. So what happens is this is becoming 60 and this is becoming 20. So basically it is killing me 80 degrees Celsius. So this is the steady state. Okay, so because we neglected the transient term and then we found the solution. When you have the transient term, it is not straightforward like this. So I mean, by now you must have noticed this is nothing but your um, uh, yeah. If you simplify your steady state heat conduction equation with heat generation, okay, but there we had a temperature field along the x-axis. Okay, here we do not have we are taking it to be one temperature. Basically we are doing lumped capacity analysis. Okay, that is something I think I forgot to mention here. So why we need to do is we is it mentioned here, when the chip is energized, however temperature increases to, for purpose of analysis, it has a uniform heating, number one, an infinite contact resistance between chip and substrate, and negligible conduction resistance within the chip. Okay, so there is no conduction resistance within the chip, which means the entire chip is going to be at the same temperature. Okay, whenever there is a small heating, it is going to be felt everywhere because the resistance to this conduction is very less, negligible. Okay, which means we no need to really worry about how the temperature field is varying within the chip. We can directly take this entire chip to be at the same temperature or isothermal chip. Okay, and then it becomes a lumped capacity analysis way of modeling this. So that is what we are doing. That is why we did not have uh, for example the heat conduction, okay, term. So ka dt by dx is not here. All right. So basically this is the steady state temperature it reaches when you have heat generation of 9 into 10 power 6 watt per meter cube. Now the second thing that we are asked to find is what is the time taken to reach 1 degree Celsius less than this steady state temperature, which means time taken to reach 79 degrees Celsius. What is the time it takes? Okay, once you switch it on, how much time does it take to reach 79 degrees Celsius is what they're asking. So now, since time is also here, we cannot, remove the dt by dt term. We cannot basically remove the transient term. So you are going to have the entire equation for the analysis over here. You will have q dot g rho c minus HAS by rho CV times T minus T infinity. This is your equation. Now, how would you, one second, yeah. Now, if you want to uh, perform this analysis, you basically need to integrate this. This is a, ordinary differential equation. We no need to go into method of separation and all. Right? So this is something we already know. Q dot G by rho C we already know. HAS by rho CV is also going to be a number. It's T minus T infinity. Okay, T infinity we already know. So basically you have a uh, ordinary differential equation which is just a function of time. Okay, so now let's say I am going to, so to simplify this analysis, maybe we can do a change of variables. So theta is nothing but T minus T infinity. If you do, what happens, the d theta by dt, if you want to do, that is going to be simply dt by dt, because t infinity is constant. So basically I'm differentiating this to here. So I can replace this dt by dt to d theta by dt. Okay, and then I can write this q dot, this is same, minus HAS by rho CV. So t minus t infinity I can replace it with theta. Okay, so this is just for simplification for our to easily get the solution. Now I can also simplify it further. Instead of this intimidating rho c h as everywhere, I can just make it as, we know it's a constant, like we know all the way parameters, so I can just write this as a minus b theta. Okay, So basically you need to solve this differential equation. What is A? A is Q dot G by rho C, and B is HAS by rho CV. Okay. Now, how do you solve it? You just need to integrate it, right? That's it. So you take the all the terms containing theta to one side and all the other terms containing t to the other side. You'll end up having it. You just integrate it. Now, while you integrate it, you can either you know integrate using indefinite integrals. You can apply initial condition, you can get a solution, and then you give a temperature to find the time. Either you can do that, or you can use definite integral. You can just say I want to go from theta I to some theta final, but this theta final should be 79 degrees Celsius. That's all. Similarly, I want to go from 0 to t. So basically you are trying to find out this t. Okay, so theta I is nothing but Ti minus T infinity. Initially, your chip is at 20 degrees Celsius, so this is going to be simply 0. T infinity is also 20. And theta F is nothing but your desired temperature, which is 79, not 80. It's because that is what has been asked. We want to know the time it takes to reach, to come within 1 degree Celsius, okay, of the final temperature. Now, if you do that, it is going to be T final minus T steady, sorry, T infinity, sorry. T final is 79, we are interested, minus 20. Okay, so this would be, I guess, 59. So that is what I need to do. I need to go from 0 to 59. D theta divided by A minus B theta is equal to integral of 0 to T dt. Okay, so these are basic mathematics. That's why I'm going a little fast. If you have any doubts, please stop me at any time. Okay, so now if you integrate the left hand side, what would happen? It's nothing but it is in the form of dx by x, right? So it's like 1 by x integral, which you know it's going to be a natural log of, you can write a minus b theta, and whatever the coefficient of theta, we will write it in the denominator, right? This will be from 0 to 59. This is how you integrate it. And then if you integrate dt, it's going to be simply t minus 0. We are just eliminating 0. So once, if you evaluate this thing, that's all, your problem is solved. You just need to know this time only. Okay, for that we need to know a and b. Let's evaluate a and b. A is q dot g by rho c, right? Q dot g by rho c over here. Let's calculate that. Q dot g is 9 into 10 power 6 divided by rho is, I think, 2000, and c is specific heat constant, which is 700. So now let's say if you perform this calculation, you will end up having something like 6 point. Please check this. I might be making mistakes in between. I'm not very good in calculators. And then finally you have B, HAS by rho CB. HAS by rho C. H is 150. AS we saw it's 25 millimeter square, so I am going to multiply it with 10 power minus 6. Rho is 2000. C is 700. And volume is again 25 meter cube, so it's going to be 10 power minus 9. Okay, so this you can cancel them. So we can cancel this, and this also, and then this and this you can cancel, so it becomes 15 by 140, which should be 0.1071. This is your A and B. Now let's substitute these values. So time here is nothing but logarithm of A is 6.4286 minus 0.1071 theta divided by minus 0.1071 from 0 to 59. Okay, So now if I want to substitute this also, 6.4286 minus 0.1071 times 59 divided by minus 0.1071, and then you subtract it with natural log of 6.4286 minus the b times it would be 0, so we can just remove that, divided by, sorry, divided by minus 0.1071. Okay, so now if you perform this analysis, what would happen? 6.4286 minus 0.1071 times 59, natural log of this divided by minus 0.10, this is coming to be 20.63, and this part is 6.286. If you have found the answer, please let me know. 0.1071 times 1 plus 20.6. Yeah, okay, so it comes out to be something like 38 seconds. Okay, so now if you want to perform, let's say if I want to know how much time it takes to reach steady state, okay, what will I do? I'll just change this 59 to 60 and I get the steady state value. That's it. Okay, or let's say if I want to reach 30 degrees Celsius, from 20 I want to know how much time it takes to reach 30. Okay, you just change this T final to 30 degrees Celsius, you will end up having your answer. Okay, 30 minus 20 would be 10. So theta f would be 0 to 10. You will integrate it from 0 to 10. That's it. Okay. All right. Yeah, one more thing I think I might have misspoke, or maybe you can find out. So let's say if I want to find what is the time it takes to reach steady state, okay, which means I want to go till theta f equal to 60, which means I want to go till 80 degrees Celsius. So how would you find that time? If you change this to 60, would it work? Is something you try to answer by yourself. Okay, I will just leave it to you. All right, so this is what is being asked here. One thing is we need to find steady state, which we found it to be 80 degrees Celsius, and the other thing is the time it takes to reach near to steady state is 38 seconds. Okay, now but we should remember one of the assumptions that we made that chip is, there is the contact resistance between the chip and the substrate is very high, right? So which means none of the heat is traveling from chip to substrate, but in reality that will not be true, right? So since you have like 1 mm deep, the chip is 1 mm deep into the substrate, and also substrate and chip is not going to be have infinite contact resistance. It is going to have a little bit contact resistance, but the chip is going to give away some heat to the substrate. There is going to be heat conduction, right? And if that is the case, uh, how would your final temperature would change? And similarly, if I want to know how much time it takes to reach nearby steady state, uh, how would I do it? Okay, so that is basically your second question that I have here. I'm asking, in addition to treating heat transfer by convection directly from the chip to the coolant, a more realistic analysis would account for indirect transfer from chip to substrate, right? So whatever we did till now is not realistic because we neglected the heat transfer from the chip to substrate. Now, the realistic analysis would include that heat conduction also. So and also that not just it does not stop there. If you go there, so this is your chip, and if chip is getting heated, the there is going to be heat conduction to the substrate. Okay, in all these direction, in all the four direction, there's going to be heat conduction. And in addition, what also happens is this fluid which is flowing here, right? The fluid does not just only pass through chip, it is also going to pass through a little bit of substrate. Okay, so which means there's going to be some more convective heat transfer with the substrate also, and that substrate's heat is also actually coming from the chip. So chip is going to give some heat to substrate, and the substrate is going to take away that heat and give it to the fluid which is going on top of it. Okay, so that heat also we need to account in order to have more realistic analysis. That is what they are telling. The indirect heat transfer from chip to substrate, and then from substrate to coolant. From substrate also to coolant, there will be some heat transfer. Okay, only if you consider this, this would be more realistic. The total thermal resistance associated with this indirect route includes contribution due to chip substrate interface or a contact resistance. So there is also another contact resistance also, and multi-dimensional conduction in the substrate and the convection from the substrate to the coolant. So performing this analysis would require you to resolve contact resistance, and you saw from different, since it's a square, you're going to have four surfaces and also bottom surface which is in contact with the chip, right? Sorry, which is in contact with the substrate. Now if all these surfaces is going to give away heat to this substrate, it is not going to be a simple one dimensional problem, it will be a multi-dimensional problem. Okay, and performing such an analysis requires an a computer to perform. Also you may need to use some CFD techniques and things like that. But instead what we are going to do here is, let's say if I give you the resistance, the total resistance from all this, let's say somehow I did the analysis and I got the resistance. Okay, if this total thermal resistance is given, okay, now how would you calculate the steady state temperature, and also what would be this um, time taken to reach nearby steady state? So that is what they are asking. So basically, let me, maybe if I draw it, it would be more clear. We know this is the chip and this is going to generate heat. Okay, now there is a convection heat transfer from here to here, Q convection, which is what we accounted previously, and we assume that these walls are, the resistance is too high, so heat cannot go here. So basically these are adiabatic, we assumed it to be adiabatic. Now what I'm trying to say is, now from here the heat conduction happens, here the heat conduction happens, here the heat conduction happens, and in addition the heat convection, the convection also happens here. Okay, let's say we'll call it Q dash convection. This is Q dash conduction. But performing this analysis by hand is going to be difficult. So we don't want to do that. Instead, let's say I know the total resistance associated with all these, with all the red heat transfer route. The total resistance, if I know, which is 200 Kelvin per watt. Now let's say if they given this information, how would you solve this problem? Is what they are asking. So basically, again, you need to, as I said before, you should have the energy equation. It, at the end of the day, everything boils down to energy equation, and there is no E dot in. We know E dot. Let me, for the sake of completeness, let me write it. E dot in minus E dot out plus E dot generation is equal to E dot store. So the E dot stored is going to remain same, rho Cv dt by T, because we are working on the chip is not changing. E dot generation is going to remain same, Q dot G into V, and however the E dot out is not just through this Q convection but also through other means whose overall resistance we know. So if we know the overall resistance, the overall heat going out of this thing is going to be simply the delta T by total resistance, right? And this delta T is happening from the chip to ultimately to the convection. So basically what I'm trying to say is there is a conduction happening and then there is a convection happening. So the delta T should be from the chip to the convection, which is again going to be T minus T infinity divided by RT. Okay. So in addition to Q convection, you also have this QT. Okay. Let me write it down. Q convection plus Q. These both are E dot out. Okay. So this is going to take away the heat from or energy from your system. So that is the only difference here. I hope it's clear to everyone. It's going to be simply H convection is HAS T minus T infinity, which we already did. In addition, we have again T minus T infinity divided by RT plus you have Q dot GV plus rho CV dt by dt. So let's simplify this also and we'll write the final governing equation that we will follow. So dt by t is nothing but Q dot G by rho C and minus it's going to be T minus T infinity into, I'm just taking this as a constant, HAS by 1 by RT divided by rho CV. So previously you should have noted that it was HAS by rho CV without this resistance. Now since resistance is given, it is going to be simply a combination of two resistance. So what is HAS? HAS is also 1 by RT. And if you look at this, it's 1 by RT, 1 by R convection plus 1 by RT, which means it's kind of like a parallel connection, right? So from T to T infinity you are going. One route is convection, the other route is indirect way of conduction plus convection. So it's a parallel routes between T and T convection. That's why it's a parallel resistance and that is what you see here. Okay. Even though we derived it in a different way from energy equation, you can also relate it to uh, the energy, sorry, the electrical analogy. From there also you can try to reason this out. Okay. So HAS is also 1 by R convection and this total is going to be 1 by total resistance R dash total. This is the total resistance for the entire heat conduction from the chip or heat transfer from the chip. Okay. So if it is 1 by R, it's going to be conductance, right? That is what we write it on the numerator. Okay. I hope the physical significance is also clear. Basically, okay, this is our final equation. And now we are going to do the similar analysis. So once you find the equation, the analysis is simple. It's as simple as that. Now, how would you do it? Now, first thing is we need to know steady state temperature. So for steady state temperature, we just make the dt by dt to be 0. So then what would happen? We just write Q dot G by rho C is equal to T minus T infinity into HAS plus 1 by RT divided by rho C. So rho C we can cancel. We are interested in T, right? So T here is T steady equal to T infinity plus Q dot G V divided by HAS plus 1 by RT. This is what it is. Okay. So basically we had only convection resistance. Now in addition we have the resistance, total resistance from the indirect route from conduction and then convection. All right. So let's try to find out this. This T infinity is 20 and Q dot G is 9 into 10 power 6. You already know it's going to be 25 into 10 power minus 9 divided by H is 150, area is 25 into 10 power minus 6 plus 1 divided by RT, which is 200. Okay, you can also compare the what you call the units. So you can compare the units of HAS and you can compare the units of 1 by RT. Okay, and that is going to remain same. Basically HAS is 1 by R. All right, let's simplify this. How much should that come out to be? So 150 into 25 into 10 power minus 6 plus 1 divided by 200. I guess it's 200. So total resistance given is 200 Kelvin per watt. All right, and 9 into 10 power 6 divided by 8.75 divided by 10 power minus 3 times 25 into 10 power minus 9 plus 20. So this comes out to be, so please note this. So now when you include those heat dissipation also, your chip temperature reduces to 45.71 degrees Celsius. So this makes sense, right? So you have increased your capacity of removing heat from the system. Okay. In this case, your system is chipped. And so your steady state temperature, which was 80 degree when you don't consider this heat transfer, now it has reduced to 45. Okay. All right. So this is more realistic value compared to the previous value that we got. So now the second part, same as, let's say I want to reach time taken to reach time taken to reach within 1 degree Celsius. So within 1 degree Celsius means, let's say 44.71 degrees Celsius is what I want to get within 1 degree Celsius of 45.71, which is 44.71. How much time does it take to reach 44.71? Okay. So this is going to be transient analysis. So we will use the entire equation. However, we will now transfer the variable before we use it. We'll write t minus t infinity. And if you differentiate this with respect to time, it is going to be simply dt by d. So we can write the dt by dt equation to be in terms of d theta by dt is going to be simply q dot g by rho c minus HAS plus 1 by RT times theta divided by rho CV. Okay. So what I'm going to do is, again I'm going to simplify it in terms of A and B, because we already know all these variables. For example, B is, let's say for the, since we already used B in the previous problem, I'm going to use something like B dash, which is HAS plus 1 divided by RT divided by rho CV. We know all these parameters. It is coming from the properties and the convection coefficients. So now if you do this, what happens? Your equation gets simplified. It becomes A minus B dash theta. And we just solve this similar equation. So we can make a, let me write directly what is the theta is. Or, you know, we are differentiating it, right? So d theta divided by A minus B dash theta equal to dt. So we are going to use similarly definite integral. So it becomes theta I to theta f. Here theta f is going to be tf, which is t desired for you, not f doesn't mean final. Okay, the final is steady. So this is going to be tf we are interested in till 44.71. This is T infinity is 20, so this is going to be 24.71 degrees Celsius. Now theta I is nothing but Ti minus T infinity. Initially chip is also the same temperature as the liquid, so it's going to be simply 0. And what we need is, we need this time. This is what we already did before, so I am just repeating. So we can write T to be integral of 0 to 24.71 d theta divided by a minus b dash theta. So if I integrate it, similarly natural log of a minus b dash theta divided by minus b dash, it will be 0 to 24.71. Now A is already known, I guess. A q dot g by pc is not changing. We already did in last example. What is 6.4286? It is 6.4286. However, we need to find b dash because it's not simply HAS by rho CV. Now we have additional 1 by RT term. Let's calculate this b dash first. B dash is HAS plus 1 by RT divided by rho CV. H is 150, AS is 25 meter square, millimeter square, so it's going to be 10 power minus 6 plus 1 divided by 200 whole divided by 2700. Volume is 25 millimeter cube, so it's going to be 10 power minus 9. Okay. So now, what is the value you will be getting for this? 50 into 25 into 10 power minus 6, 1 divided by 200 divided by 2000. 10 power minus 9. So this comes out to be 0.25. This is your b dash. So b dash before it was 0.1, now it's 0.25. Alright, now let's substitute it. Natural log of 6.42, what was it? 4286, 6.4286 minus 0.25 times theta divided by minus 0.25, and we are integrating from 0 to 24.71. Alright, let's put everything together. Log of 6.4286 minus 0.25 into 24.71 minus natural log of 6.4286. So 0.25 times 0 is 0, so I'm neglecting that, divided by minus 0.25. Now if you perform this calculation, 6.4286 minus this natural log of this divided by minus 0.25. So I'm getting time to be something like 5.52 seconds. I might be wrong. Let me calculate it again. If you guys found the answer, please let me know. Natural answer. I think I forgot to do. Yeah, it's 5.2. Only this part is 5.52. Forgot to perform the other one. So that comes out to be 12.97 seconds. So which means 13 seconds. Okay. So which means you have basically increased your heat transfer. So since you have increased your heat transfer, you can quickly reach the steady state. So before it was 38 seconds, now it's reduced to 13 seconds. So within 13 seconds, you can reach close to a steady state temperature of 1 degree Celsius. Okay. But how do we know the resistance is 200 Kelvin per watt? That we don't. It's already given in the question. That's why we took But getting that 200 requires a lot of knowledge, or maybe you may need to run a separate, uh, multi-dimensional simulation to get that value. Okay. So in our uh, question, it is simplified and they have given directly the resistance. So we are lucky. But in general, let's say if you're performing such an analysis, let's say if you're going to an industry and performing such an analysis, then you may need to perform a multi-dimensional approach in order to find out what would be the effective heat transfer rate from the system and how much time it would take to reach the steady state. Okay. All right. Um, that is what I have today. Um, so basically, we did this transient heat transfer analysis, but not for a general geometry like sphere. If you have, some different geometries, this actually it does not depend on geometry. It basically came from the energy conservation, right? Energy conservation. We did not write any differential equation dt by dx, dt by dy. We never wrote that, right? So this is for the entire system. Let's say if we take chip as a system and it has only one temperature, so that is the main assumption. It is having one temperature, which is basically what the lumped capacity analysis means, right? So when you have such an analysis, you can take advantage of it by just writing an energy equation for that system and try to find out what are the heat transfer going out of the system, and also whether there is any heat generation. You add them, and then you you end up having the energy equation. And given this energy equation, you can perform steady state analysis, you can perform transient analysis, uh, whatever you wish. Okay. But first assumption is the main assumption which will lead to this is the entire chip is at same temperature, or within the chip there is no difference in the temperature. Okay. Negligible conduction resistance, basically that's what it means. All right, I hope there is no question. Thank you Avinash, Shivam, for joining. I think couple more also joined in between. um, if you guys have any questions, I would be happy to answer uh, regarding the question that we solved, or if you have any questions regarding the uh, what you call the lecture materials. If you don't understand certain derivations, if you don't understand certain concepts, you can also let me know. I would be happy to clear that concepts for you. All right, that is from my side today. I hope this would be helpful for you to solve your assignment. I guess your assignment this week is also transient heat transfer analysis. So if you have no doubts, then we can meet next week with probably a convection problem. All right. Thank you, Avinash Shivam, for joining. And also thanks for whoever is going to see this video in the YouTube. I see a lot of views for my videos, but I don't know why you guys are not joining the session. Anyway, no problem. If you have any doubts, let me know. Either through email, or you're welcome to come join the next session. Thanks, Avinash. Bye bye. Will I will stay here for another 30 or 40 minutes if someone wants to join and ask a question. Uh, yeah. My email ID is, so it's Ganesh KV at iitgn.ac. Okay. Okay. This is my email ID. So if you want to if you have any questions, you can email me. I will be able to respond to you. All right. Thanks. Bye bye.